Hello, in this video I will be talking about Lab 1, which focuses on Newton's second law. In this lab, we were tasked with recording an object moving at a constant velocity, which means moving at a constant speed and in a straight line. This is useful to us because if we know that the object is moving at a constant velocity, and we know that velocity, then we can predict its future positions just by knowing its time. In my example, I recorded a ball rolling on a wood floor. Now, if we assume constant velocity, then we also must assume that there is no net force acting on the object, which means no friction, no air resistance, and a completely flat floor. Here's a video of the ball rolling. I imported this video into Tracker and I plotted its x position versus time on this graph. The change in velocity of an object can be calculated by multiplying acceleration by the change in time. If delta v is constant, if the velocity is constant, then delta v must be 0, and therefore the acceleration must also be 0. Plugging in a equals 0 to the second equation, we get force equals m times 0, or force is 0, the net force acting on the object. This graph is particularly helpful in visualizing the lab because its slope is the velocity of the ball. And as we can see, the slope is fairly constant throughout the graph, which means that the velocity is almost constant in real life. And the graph has a negative slope because it's moving to the left. The ball, I set the x-axis, positive x to the right and negative x towards the left of the frame. And as the ball was moving left, that means that it got further and further away from the origin. Now, if I switched that and if I made positive x to the left and negative x to the right, then the graph would look almost the same. It would have a positive slope instead of a negative slope, but the value of the slope would be the same. The ball would be moving at the same speed, but just have the negative velocity of what it has now. I also plotted and made a model of the ideal motion of the ball with no net forces acting on it. And this is that video. As you can see by this graph to the right, the blue line, the predicted position, matches almost exactly with the orange line, the observed position. And I calculated the predicted position by finding the average velocity, which is the final position of the ball minus the initial position of the ball, over delta t, which is the time interval that I was recording for. Now this is how the ball would move under ideal conditions with no net force. And it's impossible to determine the exact number of forces acting on the ball to create this net force, if there is one, because there are so many possible forces that could be acting on it. For example, air resistance, friction, and uneven ground. There may have been bumps in the wood, and air from my air conditioner and heater. Now the slope, as you can see in the middle part of the graph and towards the right of the graph, doesn't match exactly. This could be for various reasons. For example, in the observed motion video, these forces most likely do exist, and they could have affected the velocity and position of the ball. To improve this experiment, I could have placed the points more carefully on Tracker. I could ensure that there is even spacing between them if the ball was truly moving at a constant velocity, and I should place the points in the center of mass of the ball. I tried doing that, but it was sometimes hard to tell where the center of mass was because when the video paused, the edges of the ball were fuzzy. So I placed some unevenly spaced points which caused the curved slope that you could see in the graph. I could also minimize the outside forces acting on the ball. For example, I could roll the ball on level ice instead of on wood to eliminate friction. I should also ensure that the ball is perpendicular to the camera, because if the ball is rolling at an angle, then it may be hard to tell the exact position that the ball moved over a certain amount of time. Thank you.